right, while he sets up, our final presentation of the conference is Maciej Besta from ETH Zurich.
Okay, welcome. Can you hear me? Wonderful. So welcome to my talk. I'm Maciej. I'm a researcher from Thorsten Heffler's group, and I'm going to present a sort of summary of a long-term project that we did together with our friends at CSCS, and the outcome, like the most recent outcomes of which we published at NSDI, about building, deploying, and routing a real testbed of the Slimfly interconnect. Okay, there's this. So just a few words about myself. So I'm Maciej, and I'm interested broadly in irregular sparse computations, such as graph computations, which means doing anything from processing to storage to analytics on complex large data sets in domains such as LLM ecosystems, such as sparse tensor computations, especially in the context of recent large language models, but also other domains like graph neural networks, graph compression, different types of graph algorithms or systems and infrastructures. But not just into these workloads and applications themselves, but also how to run these things efficiently and effectively on the underlying resources, including different types of massively parallel systems or heterogeneous resources. And also how to make these things more performant, more scalable, able to scale to large data sizes, but also easy for developers to think about, to reason about, and to develop. So today we are going to speak really about this lower part of this picture, the interconnects. So just a very brief intro. As you all know, networks are crucial for performance of basically anything that we are running these days. For some numbers, some example numbers, networks can constitute up to 50% of the total power consumption of a large compute center, or even up to 1/3 of the total construction cost of such a large center. Right? But we do have many different ways of connecting our resources, our routers, servers, and endpoints into networks, as well as routing them. Right? So which one do we actually select as the most cost-effective, as the most performant? So we are going to take a detailed look at one of the topologies that we designed over the years. But before we take a look at this topology, let's take a look at the setting we are going to deal with. So we are going to deal with the direct network setting, where we have switches or routers. So our schemes are sort of orthogonal to whether we deal with routings or switching. We have some servers attached to each of these routers. And then we have the topology of the switch-to-switch or router-to-router links that we are going to focus on today. We are going to take a look at different aspects of this topology. In the first part of the talk, we are going to take a look at how we actually cable, how do we connect these switches together to form these networks, and then how we actually build this real testbed from that construction that we proposed. In part number 2, we'll take a look at our routing protocol that we developed, and then how we implemented this using the InfiniBand architecture. And then, of course, some results on some of the most interesting workloads that we have these days, as well as some summary of the broader efforts we conducted on this testbed and potential plans for the future, or ideas for the future. So Slimfly is kind of the central name here, so let's take a look at what Slimfly actually is. It's a network topology, so this topology of this inter-router or router-switch link that we proposed some time ago. And the key idea in this network is really to lower diameter. What does it mean? Lowering diameter, which means the maximum number of hops between any two switches in the network, means that you also have lower average path length. That means, intuitively, that you have fewer cables and routers necessary to route your traffic. Right? So intuitively, it means that if we have some network that consists of our routers and endpoints with some cables between them, so this network here, for example, could have a diameter 3. So we have these two endpoints that you can see marked with red color. They need at most 3 hops to talk to each other. Right, so the key idea was to lower the diameter, for example, by recabling this network, which means removing, in that case, removing some of the routers, at the same time increasing the endpoint density at the remaining ones to have the same size network, and then recabling so that you have lower diameter. Right? In that particular case, we have now diameter of 2, because these two endpoints only require 2 hops between their switches. Right, and again, the intuition is that we have lower diameter, lower average path length. So that means on one hand that we have fewer hops, which gives us lower latency. Right? So that means higher performance. This is kind of obvious result, but the other, a bit less intuitive result is that, or consequence, is that with fewer hops, our packets have to traverse fewer routers, fewer buffers, which means they use fewer resources. So that translates to lower cost of construction because we have fewer resources on average, and also translates to less power consumed because, again, we traverse fewer of these buffers. right? So, and now this was the key idea for how to in general approach this network design, but then the key method for achieving this, because now the question is how do we actually rewire this network or cable from ground up, right? So the key method was to optimize towards the so-called Moore bound, which is a very elegant notion from graph theory, which is really in the given graph with your diameter d and radix k. In our network setting, it translates to diameter and the number of ports in your switches. It's the upper bound on how many routers we can put in this network, right? So, for example, if you have, what is this Moore bound? Is that if you take some arbitrary switch in the network, it adds 1 to the Moore bound expression. It has k neighbors, because we have k ports, right? So it adds k to the Moore bound. And then each of these neighbors may have up to k minus 1 other neighbors, so that adds another k times k minus 1, and so on, and so on, and so on, till we arrive at the value of the diameter, right? So that's really the Moore bound. And now the idea was to optimize the structure towards this Moore bound. And that meant we, for example, fix our diameter to be equal to 2, which is what we thought was the right trade-off in terms of cost effectiveness and performance. Fix the radix to k to match what we have with our hardware, match our number of ports. And with this Moore bound optimization, the network gets as many routers as possible for this given 2 parameters. So that means we minimize the cost per router. Right? And then, since the Slimfly introduction, we have seen a lot of different efforts to parts of which we ourselves contributed in terms of developing kind of follow-up topologies, right? So we have seen designs like Expander, Galaxyfly, Megafly, Bundlefly, Polarfly, Spectralfly, and more of these networks. They are all sort of similar in that approach that they optimize towards this Moore bound or some variants of it. And all of these networks look kind of complicated, right? We have this notion of the Moore bound, which sounds not very intuitive, not very nice. We have different mathematical structures we have to use to build these networks, like Galois fields, finite fields. We have to construct some generator sets. So it all sounds like it's actually very complicated. So the question that we try to answer is it really that complicated? And can we really build these networks in practice and route and use them in practical settings? So the answer will be basically yes, as you can imagine. But for this, let's first take a look at an example Slimfly topology, at actually how it looks like. So the intuition behind the structure is that we have two subgroups, so two subgraphs, or two parts of the network. Each of these parts is consisting of identical groups of routers. So we can see that we have these groups of routers on the left, on the right, and they are the same here and the same here. Right? So now the interesting thing is that these subgroups are not connected within each of these subparts. So there is no connections between these groups here and no connections between these groups on the right side. But they are very heavily connected across this partition that divides us into these two types. So they actually form a fully connected bipartite graph. Right, so that's really how Slimfly looks like if you take a look at it from the graph theoretical perspective. And to build that and to actually cable this properly, you have to use a bit of these structures, like you have to construct a certain finite field and then do something more. I will skip that, but it's not really that complicated, as we'll see. What we did in this first part of the whole project was to actually build this in practice into the real cluster, consisting of 5 racks. And the whole cabling was basically a few months' effort over 2 days. It was not really that much. So how did we actually achieve this? So the scheme here is to kind of take a look at these subgroups again and mix them pairwise. So we are now not really taking a look at this thing from the bipartite graph perspective, but we take these subgroups and we just mix them. Right? So we now see these subgroups kind of, they are mixed. This on one hand, in general, will reduce the cable length because we now have more cables between these subgroups that are next to each other. And on the other hand, we can now actually see that we can now build racks or kind of groups in this network from these subgroups. And these groups are going to be the same because we mix these subgroups pairwise. Now they are also connected internally because there are connections between these subgroups. And these are going to form our racks. And the nice feature about it that we discovered is that actually now these racks form a fully connected plane graph, not bipartite, but the normal graph, right? So that even further simplifies the layout. So now how did we do this in more detail? So we have now one of these groups that will form a rack. And basically we have still these kind of two subgroups, right? And we realized that we can nicely fit this whole group of routers consisting of two subgroups within this rack. We can put one of the subgroups on the top part and one of the subgroups on the bottom part. They nicely fit in this rack. Then in the first step, we wired the intra-subgroup connection. So we wired each of these two subgroups at the top and then at the bottom individually. Then this is step one, right? Then we wired the subgroups within each of these racks, right? So then we have also these connections between the subgroups, and we did this wiring here. And finally, in the third step, we had to wire these racks themselves, right? So that they form this fully connected graph. And again, the structure of Slimfly was intuitive in this respect that it was easy because we had these kind of very consistent steps, very obvious steps that we could use one by one to simplify the whole wiring process. Right? But then, of course, it's not that easy because you will miss some ports, you will mix something with the cable. So you need to find a way to actually verify your design to be able to debug this deployment process and make it smooth. And here it turns out that the Slimfly structure again facilitates that, because we can also see this structure through the Cartesian grid perspective. So we can take a look at now this whole structure here. And we can see each of these parts on the left, on the right, as basically points on a two-dimensional space. So each of these routers now is described by basically a triple of numbers. And all these routers on the left have 0 as the first coordinate because they lie in the left part in this left subgraph. Each of these routers on the right side has now 1 as the first tuple element because they lie in the second subgroup. And then 2 remaining numbers in each of these triples basically is the XY coordinate in this whole picture here. And now the way that you connect these can be also described by simple algebraic equations. So you now basically operate using these triples of numbers, and you basically, for any two routers that have these coordinates, you can just say if they are connected or not based on certain conditions that relate to these coordinates. Right? So it was actually very useful because once we placed all this equipment inside this whole thing was placed inside the racks and set up using the InfiniBand implementation, then basically we could easily verify the correctness of this wiring using a simple Python script that gave a very clear answer based on these equations, whether given cabling is correct or not. Right, so it was very straightforward, and furthermore, using this whole structure, we could also generate scripts that produced nice diagrams that, with even the port numbers guiding the people that connected all these elements to do it properly and to debug even easier. Right, so that's part one. This is how we actually deployed or like constructed the network. And now let's move to part two, which is how do we actually root this design. So let's start with how do we root in established designs such as fat trees. Right, so in general, high-performance routing there is enabled or facilitated by having multiplicity of shortest paths between two different endpoints or two different routers. Right? So basically, how we achieve high performance in, for example, fat trees, that we can use multiple paths between source and destination. So here, if we have these two endpoints marked with the blue color talking to each other, if the one on the left wants to send some packets, we'll use some scheme that will distribute these packets over these two shortest paths on the way to the destination. Right? That's how we can increase our throughput of communication between any two endpoints. And now we do have lots of established techniques in the field on how to do this, usually based on ECMP. Lots of them are out there, and the question was, how can we do this in Slimfly as well? Right? Because we need this to achieve high performance. Before we continue, let's take a look at the motivation again in more detail, because we'll kind of need it to understand the exact things that are going on there. So the problems that we have to tackle with multipathing are basically so-called flow collisions. So what happens is that, I mean, there are more problems, but let's say the most serious one is flow collisions, right? So, or one of the serious ones. So if we have some workload, for example, we have two endpoints talking to each other, we can map them like this, and we have basically no problem because they just talk to each other and there is no collision. But for example, if we map two pairs in that position, so if these two pairs of endpoints that talk to each other sit on these two routers, then we'll have one flow collision because there's like one collision between two flows. Or even worse, if we have three pairs talking to each other, then we have two flow collisions. That's how we basically count it. Right? So that's a problem that we solve with multipathing. So in that case, we can easily take now these different flows and reroute them across other parts of the network to accommodate all of these flows and achieve maximum throughput that we can have in that setting. Right, so now the first question that we had was basically how many multiple paths do we need to tackle flow collisions, right? Because, I mean, obviously you have a limited number of resources, you can have infinite number of these multiple paths, and also how many do we actually need? And in one of the concurrent works that we did together with this project, we have a bunch of key insights for that specific question, and one of these key insights is that we need 3 disjoint paths per router pair to handle nearly all of the colliding flows that you can think of in a wide range of workloads. So in that work, we took lots of different workloads, and actually not just Slimfly, but also other networks beyond Slimfly, and we tried to understand what is the path diversity that we need to route properly over a given network. So key insight number 1 is that we need 3 disjoint paths for every router pair to accommodate these flow collisions in almost all of the settings that we care about. And then the second question is, okay, this is how many we need, and do we actually have enough, right, in our networks that we want to build? So here's key insight number 2 from that same work, is that in most cases, if we want to consider shortest paths, then the answer is no. So there is very few shortest path, there is not much shortest path multiplicity in Slimfly, but also in other of these networks, like Polarfly or Polarstar. So they really have almost always just one shortest path between any two endpoints. However, they have actually quite some multiplicity of almost shortest path. And when I say almost, I mean diameter plus 1. So if diameter of Slimfly is 2, then if we consider paths of length up to 3, then actually there is more than enough to accommodate these flow collisions. So that means that we have to build a routing protocol that is really multipathing, that does multipathing, but also multipathing over not just shortest, but also non-shortest paths. And that's what we basically did here. This is like a so-called layered routing protocol. And why layered? Because the key idea here was to distribute and encode different paths across so-called routing layers. So sort of different layers of the network that come with some resources in this network that we can use to accommodate a given path between 2 given routers. Right, so for example, let's take a look at these three layers here. In our convention, we use layer. So each of these layers basically is the whole topology. So we have these 2 endpoints that want to talk to each other. And now we assign different paths to different of these different layers that we have here. And now layer 0 holds minimal paths because we still have them. I mean, we don't have many of them, but we still have some of these paths. So we keep this layer for these minimal paths. So in that case here, for example, this would be this path that goes via this one router here. And then higher layers are devoted to maintaining non-minimal paths, right? So we consider as this pair of endpoints has the path length of 2, then for these 2 layers we use paths of length 3, right? And we have more of them. As I mentioned, this other work shows that we can actually find a lot of these non-minimal, almost minimal paths in these networks. So we can, for example, use these 2 other paths here. And combining these things, we have 3 paths that we need to accommodate these flow collisions, right? And there's of course more stuff beyond that because we need to kind of find these paths and do this properly so that we don't have too much overlap. Because now these paths, we need to do it for all of the pairs of routers, right? So there will be some overlaps between these paths. We want to minimize that. So there are some heuristics for minimizing that we did. So all of these details are in the paper. And but now let's continue. Because what is also interesting is that now this is the kind of the conceptual routing protocol, how it works at the high level. But then we had to put this in the InfiniBand setting, right? So we did have some problems there with that stuff. Let me give a summary of that as well. So the first problem was that, okay, how do we actually do it, right? Because now we have this concept of layers, but then we have InfiniBand that comes with its own implementation challenges, constraints, many different things, and how do we actually build these layers within this setting? And here the idea was to basically assign multiple local identifiers for the same endpoint to encode multiple paths, right? So in InfiniBand, we have destination-based routing, and in that case here we can see our Slimfly again. For example, we have these 2 endpoints with IDs 100 and 200. Right? And we have some routers on the way that we mark. So, for example, now to populate this, the forwarding entries for switch number 1 here, let's say that we have destination LID 200, so we have a packet that goes to this endpoint here. So, of course, the entry will be next hop. As we encode here minimum path, the entry would be the next hop is 3. Right? So this is kind of obvious. But now to accommodate these other paths, what we do, we actually assign multiple LIDs to a single endpoint, which is something we can actually do in this architecture. So we assign also the ID 201 to this endpoint here, and then if we would like to encode now this almost minimal path here, so now if the switch number 1 sees destination LID to be 201, the next hop will be 4. Right? So this is basically what we do globally for all of these pairs that we have in the network. That's how we encode these almost minimal paths, by using multiple LIDs for a given single endpoint. Another problem was, okay, how many layers can we support? Because now we need at least 3 of these paths per pair. Do we have enough of the address space? Because again, we have InfiniBand, we have limited address space. Is there enough, right? So InfiniBand supports at most that many unicast addresses. And now the question was, for a given number of layers, what is the largest Dragonfly that we can support in InfiniBand while maintaining also like some reasonable performance properties, right? Because we could of course do some tricks that at the cost of performance, but that's what we don't want to do. So assuming 40 ports in a switch, to maintain this full global bandwidth, in this table we can see numbers grouped in layers. So in columns. Column on the leftmost side is the number of layers that we would like to have in a given configuration. And basically, you can think intuitively, the more layers we have, the higher potential for high performance we have, because now we have more layers. That means we can have more and more of these paths. I mean, of course, the minimum is 3, but more is not bad, right? So it will give us potential for more performance still. So we run some numbers up to 128 layers, and then this corresponds to the number of switches that's the maximum we can support for this number of layers. That also translates to the maximum number of endpoints that we can have in this network. Right, so, and it turns out that to satisfy this performance criteria, we actually need 4 layers, and we can still support the maximum number of endpoints that is available in the configuration, which is actually quite nice, because that leads us to problem number 3. How many layers do we need, given that we want 3 disjoint paths? Well, we need 4 layers is just enough, right? So this is actually a very nice coincidence that with these 4 layers, we did not have to limit this maximum size of the network that we have. At the same time, we had enough of these layers to accommodate high performance, right? So, and then there was one more example problem we had to deal with. Just give me a second. I mean, can we also fail? I mean, what happened? Is it always the case that we can add an almost minimal path to this whole thing, or can we fail with this process, right? Because, I mean, we have a limited number of resources. Well, yes, we actually can fail as well. I mean, imagine the setting here that we are trying to add a non-minimal path to this layer here for the switch per 5 from 5 to 2, right? So we also want to kind of determine the way we route from this switch to this switch, which is just a single hop. But assume now that before that, we already took a look at the pair from 1 to 2, and we already accommodated this hop here, right? So because of how InfiniBand works, we can't really do it for that case here. So this is what our heuristics are to some degree trying to tackle, but there can be cases where we fail to do this. But as the evaluation shows, these are very small cases, and they don't really impact the overall performance for this workload. So these are very, very, very few instances of that problem that if ever occurring. Okay, so this is it in terms of the routing. Now let's move to part number 3, which is basically evaluation. Right, so in the first place, we wanted to, like most importantly, we wanted to analyze the performance of Dragonfly for different types of applications, including processing deep neural networks, including different scientific workloads, or HPC benchmarks such as Graph 500. And for this, we have quite an extensive evaluation, to be honest. So we, on one hand, have a theoretical analysis where we formulated this whole routing problem as the multi-flow commodity problem, and we then showed that for different networks with this routing, we do achieve very high throughput for different types of traffic patterns. Then we have lots of simulations. You can check all of them in the paper. I will not speak about simulations today, because I will focus on actually the real test beds. Right. So in the real test beds, what we did was we compared Dragonfly to the, I would say, most important competitor for that size of networks, which is two-level fetch tree, two-level non-blocking fetch tree. constructed with the same hardware that we did for Slimfly, right? So for all of these workloads we are going to see, we ran them on Slimfly, we measured all these numbers on Slimfly, but then the Slimfly was basically recabled into a fetch tree, and then all these workloads will run again on the fetch tree. Just some more details, the rank placement strategy that we use here, unless I state otherwise, is linear for both Slimfly and for fetch tree, right? So we just linearly place increasing ranks on increasing endpoints. But also we propose a new routing scheme, right? So for this, we also do some analysis on the routing itself without this whole thing, Slimfly versus fetch tree. And in routing, we compare to the important baseline, which is like the standard baseline in InfiniBand, deadlock-free, single source shortest path protocol for routing. So let's start with micro benchmarks. So we compare different MPI collectives here, and in each of these heat maps, so the left heat map is dedicated to MPI bcast, and the right one is dedicated to an MPI all reduce, right? And each of these heat maps on the x-axis, we can see the number of nodes that we scale. So we run this micro benchmark from 2 nodes up to 200. And the y-axis is the message size in bytes, right? So we do it from 1 basically up to 2 to the 24. And then the numbers, as well as the colors in these heat maps illustrate the relative improvement that we get or decrease of performance that we have when comparing Slimfly to fetch tree, right? So the lower the worse, the higher or the greener the better. And for bcast and all reduce, what we can see is that basically especially for this 8 and 16 node configurations, and especially for all reduce with the smaller message sizes, fetch tree displays marginal advantages. I mean, we are actually worse here than fetch tree. And the reason is that we are using here this, it's I would say more is like a conjecture that fetch tree has 16 nodes per switch, and we have only 4. Like Slimfly has only 4 nodes per switch, which means that in fetch tree we have more localized zero inter-switch hop traffic, which is actually better for performance, right? So this is why these numbers are a bit worse for us. And by the way, one important notion is that when comparing to fetch tree, we don't really like. The biggest goal was not really to show that we are better in performance, because that's very hard to do with non-blocking fetch tree. The more important was to show that we actually come with comparable performance, because for Slimfly is coming with 50% savings in terms of the cost of construction. So for a fetch tree of a given size, if you want to have a Slimfly with the similar size, you need to pay 50% less to build it, right? So and that means that the main thing here is for a fixed cost to actually have comparable or if better than great, but really comparable performance was the most important measure here that we wanted to achieve, or outcome that we wanted to achieve. Right, but overall, for these two collectives, so coming back to the collectives, in most scenarios, Slimfly is comparable to fetch tree, with sometimes being somewhat worse, sometimes being better, but overall, it was not very much different. Then let's take a look at the all-to-all traffic. So here again, the same setting. We have number of nodes on the x-axis, we have the message size on the y, and again, we can see now. Okay, now we can see something different. We can see this big red blob here that shows that we are much worse for that range of nodes and for the range of message sizes, right? So why is it? So we tried to debug this, and an interesting observation was that this was actually due to traffic congestion on often in some cases, single shortest paths between few switches. And this is something that we could basically accommodate with adaptivity in routing. But the problem was that although we do have adaptive schemes that we propose in the protocol, with that InfiniBand implementation, we couldn't do it because there was like no support for adaptivity, right? So this is kind of limiting the practical improvement. However, we still found a way to actually navigate around this problem. Remember, here is what we have here is the linear placement, and it turns out that once we switch to random placement in Slimfly, we actually get even better than a fetch tree. And why is it so? So this random placement overcomes this bottleneck, and this is really the direct consequence of the fact that Slimfly, because you can think now, okay, random placement is weird because, I mean, you have random placement means you have higher latency, bad for performance, but remember, we have diameter 2, right? Our basic assumption, our basic feature of construction. So with diameter 2, random placement will not hurt you much because you don't have much to hurt anyway in the first place. Right, so that's basically how it was possible to, even without adaptivity, still navigate these performance problems. And finally, some real workloads. Right, so let's start with some deep neural networks. I mean, something that we all talk about these days. So in this a bit complicated plot, we can see 3 groups of bars. So we have a group here, and then a group on the right. So they are dedicated to 3 different workloads. So we have Cosmoflow, we have ResNet, and we have GPT-3. So they come with different forms of parallelism they harness. So for example, ResNet comes with pure data parallelism, and GPT-3 comes with a mixture of data operator and pipeline parallelism. Now, for each of these groups of bars, we scale the number of nodes, right? So from 40 to 200, and the y-axis is the iteration time, right? In seconds, so the lower, basically, the better. And then we also have these numbers on top of each bars, which indicate again the relative difference between Slimfly and fetch-tree, right? So again, the greener or the higher, the better. And now, observation number 1 is that, for example, for this Cosmoflow, we are sort of comparable, right? So we can see that it's like sometimes we are a bit faster, sometimes a bit slower, but all in all, we are doing fine. For 2 others, we see something interesting. So we can see that, for example, for GPT-3, we are actually much faster for the last 2 bars for the larger scales, but we are slower than fetch-tree for these 2 corresponding bars, the same node counts for ResNet. And now the question was, okay, but they both basically use all reduces at higher node counts. This is like the main bottleneck there, and why are we different there? But turns out it's actually consistent with our micro benchmarks, because these 2 classes of models use different message sizes. So for example, GPT-3 uses larger messages than ResNet, and this is basically what we also saw in the previous plots for these micro benchmarks, that for these 2 different sizes of messages, we have these differences. So this is all kind of consistent here across these plots. And then some HPC benchmarks, again, a similar plot where we have this a bunch of classes of bars. So these 3 are dedicated to BFS, which is the breadth first search graph traversal, the graph pattern implemented in the Graph 500 benchmark that we run here. It's one of the important HPC benchmarks, which is very, very data intense or communication intense, dealing with lots of small messages, right? So it's like a graph traversal, you have a big graph, and we also vary here. This number indicates how many, on average, what is the number of average neighbors for each vertex, right? So how many neighbors a vertex has, with how many of them it has to talk to, and that means that the higher the number, even more communication is going to happen, right? And then we have also HPL on the rightmost side. Again, we scale number of nodes for each of these classes of bars, and the performance this time is either in GTabs, which is like the measure used in Graph 500, or GFlops for HPL, right? And again, comparison to fetch-tree at the top. And now we can see overall here in this plot that Slimfly competes effectively within fetch-tree, in terms of performance. And the other conclusion is that basically it's also quite effective for scaling these benchmarks, right? So we can see that the performance doesn't drop too badly. The final evaluation slide. So we have also this novel routing where we have this non-minimal paths that we use within InfiniBand, and how does it fare against the baseline, which is DFSSSP? Well, it does quite well, even though that we have this static routing, right? We don't really have this adaptivity implemented, but even despite this, we can see that we have very consistent improvements. So here in this plot, we only do this for the DNN workloads. Here, the y-axis is basically scaling number of nodes. And again, the green color this time, and the number is the improvement of our, or the, let's say, sometimes also decrease of our routing against the DFSSP baseline. But mostly, we can see that we are doing either comparably or better. So this was the third part, the evaluation, and now the final, very brief part, number 4. I would like to also give a brief overview of other efforts that we did with this cluster and some potential ideas for potential future projects. So what we did so far was, on one hand, this one outcome, this one paper that we published on SDI about the whole effort of how we built it, how we deployed it and routed and used it, but also some other papers, for example, the Humming Mesh paper from SC 2022, which was also invited as the CACM research highlight paper, and some other work that we have basically ongoing, such as the Swing paper. And then more upcoming outcomes. And some ideas for the future would be that, for example, we have one interesting idea of the project to understand better the foundations of performance measures for interconnects. So to have a very deeper understanding into different concepts, like we have such as path interference, global bandwidth, bisection bandwidth, how do they come together, trying to maybe delve into these measures to get a better measure of performance, or for example, of locality. Another interesting idea is to basically test, because there have been newer networks in this line of low diameter networks like Polar Star or Polarfry, but also networks, for example, specifically built for deep learning workloads like Humming Mesh, and testing them would also be quite interesting. Then some other ideas, for example, something we call the HPC for free, namely enabling chip computations by trying to find more ways to fill in the idleness gaps on HP systems, something that requires developing novel batching scheduler polishes or paradigms, also something that the cluster would be very useful for. And also we have some ongoing work that we are now working on, such as developing bandwidth optimal, fully offloaded collectives. So with this slide, I'd like to conclude. So in this whole project, on one hand, we provided the way to build a real deployment, a real testbed from the Slimfly interconnect specification. We provide a way, a principled way how to do this in a very well structured steps. This we used ourselves to build this testbed at CSCS. Then we propose a new routing, the new way of multipath routing for InfiniBand that harnesses non-minimal paths along the minimal paths that we deployed as well and implemented in InfiniBand stack, and shown that actually it does work and improves performance. We provide a very extensive evaluation that covers theoretical analysis, simulations, and the real testbed evaluations, where we compare to Fed tree and shown that Slimfly, while having this 50% of cost improvement, does deliver comparable, or in some cases better performance than Fed tree. With this, I'd like to finish my presentation. I'll be happy to take your questions.